In 1659, in a letter to Karkavi, Fermat outlined his method of infinite descent and stated that it could solve several Diophantine problems. Among others, he stated that the equation x squared plus 2 equals y cubed has only one integer solution, 5 squared plus 2 equals 3 cubed, while x squared plus 4 equals y cubed has exactly two integer solutions, 2 squared plus 4 equals 2 cubed, and 11 squared plus 4 equals 5 cubed. The first case later became known as Fermat's sandwich problem, since 26 is the only integer lying between a perfect square and a perfect cube. Centuries later, Louis Mordell studied equations of the form y cubed equals x squared plus n, now called Mordell curves, to determine their integer solutions. Fermat likely introduced these sandwich problems to shed light on classical representation of primes for n plus 1 as a sum of two squares, and primes 8n plus 1 or 8n plus 3 as a square plus 2 times another square, as we'll see next. Fermat stated that x squared plus 4 equals y cubed has exactly two integer solutions, 2 squared plus 4 equals 2 cubed, and 11 squared plus 4 equals 5 cubed. Although he claimed to prove this by infinite descent, it is unlikely that he meant using the method as a literal step-by-step construction of the solutions. Rather, the idea appears to be more structural, using descent to justify writing y as a sum of two squares and then exploiting Brahmagupta-Fibonacci identity to determine the solutions. Fermat's structural observation is that every prime of the form for n plus 1 can be written as a sum of two squares, proved by Euler in 1747 using infinite descent. The Brahmagupta-Fibonacci identity then implies that a positive integer n is expressible as a sum of two squares if and only if every prime factor of the form for n plus 3 occurs in its factorization with even exponent. Moreover, all representations of n as a sum of two squares arise multiplicatively from those of its prime factors via the identity. Since x squared plus 4 is a sum of two squares, y cubed must also be a sum of two squares. By the above criterion, this forces y to be a sum of two squares, say y equals a squared plus b squared. Applying Brahmagupta-Fibonacci identity repeatedly gives two representations of y cubed as a sum of two squares. Since y cubed equals x squared plus 2 squared, uniqueness of representation of sum of two squares, up to order and signs, implies that one of the two components must equal 2. Without loss of generality, we may assume a and b positive integers. If a equals 0, then y cubed equals b to the 6th, which would be equal to 4, and so impossible. Likewise, if b equals 0, we obtain a to the 6th equals 4, also impossible. Hence, a and b are equal or bigger than 1. First representation. From this sum of two squares, one of the two terms must equal 2. In the first case, this forces a to be 1 or 2. If a equals 2, then the term is equal or bigger than 10, which is bigger than 2, contradiction. The same argument excludes b equals 2. Thus, a equals 1, giving 1 plus b squared equals 2, hence b equals 1. In the second case, the second term equals 2. If b equals 1, then a squared plus 1 equals 2, hence a equals 1. Either way, a equals b, which equals 1. Substituting into the first equation gives the first solution, 2 cubed equals 2 squared plus 4. Now we check the second representation. If a times a squared minus 3b squared equals 2, then a equals 1 or a equals 2. If a equals 1, then 1 minus 3b squared equals 2, hence 3b squared equals minus 1, which is impossible. If a equals 2, then 2 squared minus 3b squared equals 1, hence b equals 1. Substitution yields the solution 5 cubed equals 4 plus 11 squared. Finally, if b times 3a squared minus b squared equals 2, then b is either 1 or 2. If b equals 2, then 3a squared minus 2 squared equals 1, giving a squared equals 5 over 3, not an integer. If b equals 1, then 3a squared minus 1 equals 2, giving a equals 1, which leads back to the previous solution, 2 cubed equals 2 squared plus 4. Thus, the equation x squared plus 4 equals y cubed has two integer solutions, 2 squared plus 4 equals 2 cubed, and 11 squared plus 4 equals 5 cubed, exactly as Fermat asserted. Fermat stated that the equation x squared plus 2 equals y cubed has exactly one integer solution, 5 squared plus 2 equals 3 cubed. Again, Fermat claimed to have proved this by infinite descent. More plausibly, the idea is structural. A descent argument justifies writing y in the form a squared plus 2b squared, after which the extended Brahmagupta-Fibonacci identity determines all solutions. Fermat's structural observation, proved later by Euler, is that primes of the form 8n plus 1 and 8n plus 3 can be written as a square plus 2 times another square. Together with the extended Brahmagupta-Fibonacci identity, this implies that a positive integer n is expressible as a square plus 2 times another square if and only if every prime factor of the forms 8n plus 5 and 8n plus 7 appears to an even exponent. Moreover, all representations of n as square plus 2 times another square arise multiplicatively from those of its prime factors via the identity. Since x squared plus 2 has the form a squared plus 2b squared, the same holds for y cubed, and by the above criterion, this forces y to be of the form a square plus 2 times another square. Applying this identity repeatedly yields two representations for y cubed. Comparing with x squared plus 2, the square multiplied by 2 in these representations must equal 1 squared. In the first representation, this gives b times a squared plus 2b squared equals plus minus 1. Hence, b equals plus minus 1, which implies a squared plus 2 equals plus minus 1, giving a square either minus 1 or minus 3, both impossible for integers. In the second representation, we obtain b times 3a squared minus 2b squared equals plus minus 1. Again, we have b equals plus minus 1. Substituting gives 3a squared minus 2 equals plus minus 1. The negative choice leads to 3a squared equals 1, which has no integer solution. The positive choice gives 3a squared equals 3, hence a equals 1. Substituting a equals b equals 1 yields 3 cubed equals minus 5 squared plus 2 times 1 squared. Thus, the equation x squared plus 2 equals y cubed has one positive integer solution. 5 squared plus 2 equals 3 cubed, precisely as Fermat asserted. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Your support means a lot.